Okay, any questions?
Hocam hani bu çubuğu böyle koyduk ya, hızı var dedik. Hani başlangıçta hiç hızlı olmasaydı bu manyetik alanda bu bölgenin üstünde bir kuvvet oluşur muydu? Hız kazanır mı?
Well, let's see. Your friend's question is this. We were studying this system. And we had seen that if the rod is moving with a non-zero velocity v, the EMF induced around the loop was given by minus d phi by dt. Now, if v is zero, what causes the flux change? Well, if the magnetic field is stationary, nothing. So there won't be any EMF. But then the next question you can ask is, what if the magnetic field is moving, but the rod is not moving? So suppose you have, let's say, what creates this magnetic field? Well, we can assume a solenoid. Just take a solenoid with some gap. Wrap them with wires. So this will create a more or less uniform magnetic field in the gap between the solenoids, or just take two magnets. Take one magnet, another magnet. Let's say this is the south pole, this is the north pole. In the gap between the magnets, you will get a somewhat uniform magnetic field. Well, it doesn't even need to be uniform to obtain an EMF. So let's say that you put your circuit in this system. This is our rod. This is our circuit. This is the rod. And instead of moving the rod, you just move your magnets or solenoids. In that case, well, the region, this region inside the loop, inside your circuit, which has a magnetic field, the area will be changing. You see, the flux, in this example at least, the flux was defined as B times A. So if you are moving the magnet, A is changing. If you are moving the rod, A is changing. Or you can even change the B. Then the flux B will be changing, then the flux will be changing. Now, the result that we obtained was only for the case when the rod is moving. Or we have a circuit in a magnetic field, which is, and in our case at least, we were looking in magnetostatic case, the B field didn't change in time. And it was only the rod changing. But if the B field is changing, either if it is moving around, or you just change the current running through your solenoid so that the B field will be changing, that will also create a change in the flux, the B flux. So the question is, would that generate an EMF around the circuit? Let's say this is our circuit. Instead of moving the rod, just fix the rod, move your solenoids or the magnets. Will you create an EMF? Will there be light? Well, to determine this, we have to do experiment. And what experiment tells us that even in that case, there is an EMF generated. So there will be a current running through our circuit. So this equation so even if the circuit is at rest, the circuit is not moving, but the B field is changing. Either it is moving around, or it might be, its magnitude might be changing, or it might be doing both. In this case also, we have an EMF generated. Now the question, what creates this EMF? Basically, we said that EMF is the work done on unit charge. And in our earlier example of the circuit, we said that, okay, it's the rod, the motion of the rod, or whatever is pushing the rod, that is what is actually doing the work. And work on the charges, and hence creating this EMF. But now, if the rod is at rest, nothing is moving, but the B field is changing. So what is creating EMF? There's no force acting on the rod doesn't move, nothing moves, just the magnetic field is moving. And we know that the magnetic field cannot do any work on the charges. So basically, we have to conclude that, remember, the force acting on a charge is QE plus V cross B. Now, when we are saying that the force that is pushing the rod is doing the work, or the rod is doing the work, the charges are extracting kinetic energy from the rod, the interaction between the rod and the charges are due to the electric fields. So even in that case, it's the electric field that is doing the work. Now the charges are not moving, so V is 0, still B should be 0. The B is non-zero, but V cross B is 0. Charges on the average are not moving. So the only thing that possibly can do is an electric field. It's not the electric field that we were talking when we are saying that, okay, the force is doing the work or the rod is doing the work. It's not that electric field, because if you remember our discussion, basically as the charges are moving, they will be pushed to one side and they will hit the boundary of the metal, of the conductor. And when they hit the boundary of the conductor, well, this hitting is basically the action of, if you just remove one charge, the rest of the conductor is charged. You have a charge in the vicinity of another charged object, so there will be electric forces acting on the charge. But we are not talking about that electric field here, because initially the charge is not moving anyway, so it's not trying to get out of the conductor. So it's not hitting the boundary. But there has to be some new electric field in the system that is creating the EMF. So basically our conclusion is that changing B fields create EMF, electric field, sorry. So this is basically our conclusion. So before we had seen that the electric fields are created by point charges, but now there is an alternative source of electric fields. It's the changing magnetic fields that is creating this electric field. Now, in terms of the electric field, well, this equation still holds. Well, the circuit is not moving, so there's no other force than the electric field acting on our charges. So the EMF is created by this new electric field. This is equal to minus d by dt. The magnetic flux is B dot dA. Well, let me say ds. The surface is not changing. So the only thing that is changing with time over here is B. You see, this is valid for any case, whether the surface is changing, whether the B is changing, etc. This is still valid. Now I'm applying that law to a system in which the circuit is not moving. It's just the B field that is changing. So in such a case, if B field is changing, there should be an electric field created due to this changing B field. And that electric field is what is creating this EMF, the left-hand side. On the right-hand side, the magnetic flux is defined as the integral of B over the surface. And in this equation, since I'm considering a case in which my circuit is not changing its shape, the only thing that depends on time is the B field. So the left-hand side, I can convert it to a surface integral also. by using Stokes' theorem is the curl of E integrated over my surface, bounded by my loop. This should be equal to minus dB by dt integrated over the surface. In fact, this should be true no matter whether I have an actual wire in my system or not. So for an arbitrary surface, this is valid. Since it is valid for an arbitrary surface, the curl of E should be equal to minus dB by dt. It was in electrostatics. Now we are looking at dynamical systems, and we see that if there is a changing magnetic field, curl of E is no longer zero. Well, this will have another consequence though. E cannot be written as the gradient of some potential. Because if a function is given as the gradient of some other scalar potential, then its curl is automatically zero. So if there are changing magnetic fields, curl of the electric field is not the gradient of a potential. Basically, we cannot define a potential if there are changing magnetic fields. You see, the idea of defining a potential was based on the fact that now we define the potential, if you remember, V as minus V at the point R is the integral from R0 to R of E dot dl plus the potential at R0. This is in electrostatics. We could define this because in electrostatics, this integral was independent of how we went from R0 to R. And this integral was independent of how we go from R0 to R because the curl of E was zero. Now curl of E is no longer zero if B is changing. So this integral over here is not defined. So to be able to define this integral, we have to tell how we go from R0 to R. So this integral is no longer a function of R and R0 only. And hence we cannot define a potential. We cannot define a potential. The potential by definition depends on the point only. Well, you see, the idea of defining the vector potential was based on this equation. This will be true even in magnetodynamics. As far as we know. Within our experimental limits, this is still satisfied. Since this is satisfied, B is still the curl of an electric field, curl of a vector potential. Well, this fact with the previous equation, by the way, still allows us to define some kind of a vector potential, scalar potential, sorry. Or the curl of E plus dA by dt is equal to 0. But this tells me that E plus dA by dt, since its curl is 0, we can always define it as the gradient of some scalar function. So E is equal to minus the gradient of phi minus dA by dt. In electrostatics, when nothing depends on time, this is 0. And when this is 0, well, we recover the electric field as the gradient of some potential. But this potential doesn't have the meaning of some kind of an energy anymore. That meaning is lost. Now, we will study this more detail on Friday. Now, let's concentrate more on this law. The curl of E is equal to minus dB by dt. Or in integral form, E dot dl is equal to minus B dot ds. Again, keep in mind that the direction of this line integral and the direction of this surface integral, they are related by the right-hand rule. They are not arbitrary. But if you take an arbitrary closed loop, the integral of the electric field around that closed loop is always equal to, there's a time derivative, is always equal to minus the time derivative of the flux passing through the area enclosed by that loop. Well, one difficulty one faces is usually determining what is the direction of this electric field. You see, just look at this system. Let's say if we go to our reference frame, if we look at this from a reference frame in which the rod is at rest, in that reference frame, these magnetic field lines are moving in this direction. And the induced electric field should be in the vertical direction, because when the rod is moving in that direction, we know that the current is building in this direction. This is the direction of the current running in our system. Because this is the direction of the velocity of the charges, the B field is inside, V cross B is in the upward direction. So in the new reference frame, the magnetic field will be moving, which will induce an electric field. The electric field should push the charges in the same direction. So the induced electric field is in that direction. So if you can somehow identify the motion of the magnetic field lines, then from that motion you can identify the direction of the induced electric field. So if the magnetic field lines are moving in that direction, and the B fields are in this direction, the induced electric field is upward, which is the direction of B cross V. It's always perpendicular to the B field. The induced electric field will be perpendicular to the B field. Well, let's assume we have, let's say, a solenoid. This will be we have this solenoid, this is a solenoid, which carries current in this direction, let's say. What is the direction of the B field? Out of the screen, right-hand rule, curl your fingers in the direction of the current, so this is the direction of the B field. Nope, sorry, it's outward. Let's choose our coordinate axis. X, Y, and Z is pointing outward. So let's say that you adjust the current such that the magnetic field inside is always some constant time, some function of time t in the Z direction. So what is the induced electric field? So let's see. First of all, we know that the electric field lines, well, in electrostatics, electric field lines started from point charges, and they terminated at point charges. Here, we don't have point charges. So the induced electric fields, they don't start from a point. They have to form closed loops. Now, let's look at our system. It's quite symmetrical on the rotations around the z-axis. And the induced electric field will be always perpendicular to the B field lines. So first of all, they will be in this plane. They cannot just go from plus z is equal to plus infinity to z is equal to minus infinity. That is the direction of the B fields. The z has to be, the electric fields should be perpendicular to the z direction. Secondly, they have to form closed loops unless they go to infinity. And furthermore, they cannot start from a point. And we also know that our system doesn't change if we rotate our system around the z-axis. So this tells us that the induced electric field should basically form circles around the z-axis in the xy plane. Let's say E. Well, they can only depend on the s coordinate, the distance from the center of my ring, of my solenoid. It cannot depend on the phi coordinate because my system doesn't change if I rotate my system around the z. It cannot depend on the z coordinate. Again, my system doesn't change if I just shift my system along the z-axis. So the only thing it can depend on is the s coordinate. And furthermore, it should be in the phi hat direction. So that I don't know the directions, but basically the induced electric field lines will form such circles. Now let me use Ampere's law for this case. Now Faraday's law for this loop. I know that E dot dl around this loop should be equal to minus d by dt of B dot ds. Let's say the radius of this loop is s. Now the left-hand side, the electric field is E0 in the s direction times phi hat. dl is its magnitude in the phi hat direction. Since I'm going in the counterclockwise sense around the z-axis, I'm moving in the phi hat direction all the time. This should be equal to minus d by dt. Okay, b is b0 f of t in the z hat direction. ds is magnitude. What is the direction of ds? It's z hat direction. Because you see, the direction of this dl and the direction of ds are related by the right-hand rule. Just curl your fingers in the direction of dl, then your thumb points in the direction of ds, which is the z direction. Well, the left-hand side, E0s around this loop is constant. S is the distance from the central axis of the solenoid. And I just assume I'm considering a circle with center at the central axis. So S doesn't change around my loop. This I can just take out of the integral. E0s. What remains? Well, phi hat dot phi hat is just 1. What remains is the integral of dl, which just gives me the circumference. 2 pi s. This is the left-hand side. Now the right-hand side, minus d by dt. B0 is a constant, I can take it out. F of t is a constant. Well, it is time-dependent, but it is constant. You see, what is this integral? Is I'm just dividing my source into very small patches, calculating this function at all of those patches. But from patch to patch, I'm not changing the time. I'm only changing the position. So T is constant in that sense. T is constant at a given time. T is constant over all the surface. So I can take it out of my integration sign. S ds is the area of the patch. If I just sum all the areas of the patches making my surface, I get the total surface area, which is pi s squared. So let us do some cancellations. So E0, well, pi I can also cancel. E0 of S is equal to minus B0 dF by dt over 2 and S. So basically electric field is getting stronger as we go away from the center. Well, you see, we started by assuming, well, we started not by assuming, we started by showing that the electric field should be in the phi hat direction, either plus phi hat or minus phi hat. So the induced electric field is minus B0 over 2 dF by dt S in the phi hat direction. And this minus sign basically tells us that, well, at least if the B field is increasing, then the induced electric field is in the minus phi hat direction, in the opposite direction.
Hocam peki bu şeyin dışına çıksa?
Well, let's do that also. Of course, this is valid for S is less than R. The same problem. But this time, let's assume S is larger than R. This time, let me also take clockwise as the direction of my loop. I claim that it was arbitrary. You can choose whichever direction you like. So let's choose it clockwise this time. Now let's start with the left-hand side. E dot dl around my loop. Let me call this distance S again. This time S is larger than R. E dot dl will be equal to E0S in the phi hat direction. But this time dl is its magnitude times, but in the minus phi hat direction. You see, phi hat direction is again given by the right-hand rule. Just point your thumbs in the direction of Z, then your fingers curl in the direction of phi hat. So phi hat points in the counterclockwise sense at every point. So in this case, dl, since dl is in the clockwise sense, dl is in the minus phi hat direction. What is the direction of phi hat? At every point, it will be tangent to this circle, but in which direction? Plus. What do you mean plus? Yes, that's what I mean. So at this point, this is the direction of phi hat. At this point, this is the direction of phi hat. At this point, this is the direction of phi hat. And these directions I just determined by the right-hand rule. Your thumb in the z direction, so at every point, your fingers should be in the phi hat direction. But dl is pointing in the opposite direction. You see, I'm going around the loop in the clockwise sense. I chose it to be so. Arbitrary. The direction of dl is, you see, this is our law. We have to choose a loop. We have to choose a direction for our loop. Then there is an area enclosed by that loop, and we have to choose a direction for the area. The choice of the direction of the loop and the direction of the area is almost completely arbitrary. The only restriction you have is that they should be consistent. The direction of dl should be consistent with the direction of ds. That's the only restriction you have. So once you choose the direction of dl, the direction of ds is fixed. Well, how do you choose the direction of dl? As you wish, whichever direction you like. We already did one example where dl was in the counterclockwise sense. Now we are doing another example where dl will be in the clockwise sense. Well, let's see. Well, after this step, I will prove that the parallel component of the electric field to the surface of the solenoid should be continuous. That I will also prove. And then we will see that although we have chosen different directions for inside the solenoid and outside the solenoid, we will see that the result we obtain is continuous. It doesn't really matter which direction you choose. But I repeat, you have to be consistent. That's the only restriction you have. Choose whichever direction you like, but be consistent. So let's see. Well, E0S is constant around my loop. I can take that out. Phi hat dot phi hat is 1. What remains is the circumference. Well, just like in the previous case, we end up having E0S times 2 pi S. But of course, now we have a minus sign. Well, in the previous case, we didn't have a minus sign. Now we have a minus sign because we changed the sense of our loop. It's like changing the limits of integration, the upper limit and the lower limit. It introduces a minus sign. So this is our minus sign over here. Well, let's calculate B dot ds. This will be equal to B0 f of t in the z hat direction. Well, ds is, let's say, its magnitude. What is the direction of ds? It's in the minus z direction now. You see, to determine the direction of ds, you have to use the right-hand rule such that your fingers curl in the direction of your loop. Then your thumb is in the direction of ds. So ds is in the minus z direction. So you see, by changing the orientation of my loop, I received then minus sign on the left-hand side compared to the previous case. I also receive a minus sign on the right-hand side, so nothing changes. So that's basically why it's arbitrary to choose the direction of dl. So this is equal to B0 is a constant. F of t is constant in the sense that it doesn't depend on which patch I'm summing over. And z times minus z hat is minus 1. And the integral of pi ds. You see, there is one thing we have to pay attention to in this case. I said that B0 is constant in my loop, but that is not correct. You see, in my loop, this is my loop. My magnetic field is 0 here, and B0 over here, B0 times F. So B0 times F depends on which patch I am considering. So I divide my area integral into two regions. the sum over this area inside the solenoid plus the sum over the area in this rim between the solenoid and my ring. In this region, B is 0, so there's no contribution to my integral. The only contribution to my integral is from this region. And the area of this region is pi r squared. You see, this is one difference from the previous case. In the previous case, we had pi s squared. Because all the area of my ring, all the area enclosed by my ring was immersed in a magnetic field. But in this case, not all the area enclosed by my ring is immersed in a magnetic field. Only this area is in a magnetic field. The rest is at zero magnetic field. So the flux is the magnitude of my magnetic field multiplied by the area of the solenoid. Now I have my law, which states that minus E0 S 2 pi S should be equal to minus d by dt times minus B0 F of t pi r squared. I can cancel the pi's, and E0 of S is equal to minus B0 F of t over 2 r squared over S. E of r is equal to, well, if you look, we can just combine those two results. It will be equal to minus B0 f of t df, no, sorry, I have a time derivative over here, df of t by dt over 2 in the phi hat direction times S if S is less than R, and R squared over S if S is larger than R. So you see, when S is equal to R, well, both of them are equal. So it's continuous.
Ama bu şu yüzeye paralel olan.
That is the only component it has. Well, okay, we will study the continuity later on. So this is the induced electric field. The induced electric field only has this phi hat component. That is what we had agreed before starting the calculation. Well, in general, the parallel component of the electric field parallel to the surface, to a given surface, will always be continuous. Let's also prove that. You see, we have E dot dl around any loop. This should be equal to minus d by dt of B dot ds. Well, just take an arbitrary surface, consider such a loop. This is D, so that the surface goes in between my rectangle, whatever the value of D is. So E dot dl around that loop, well, let me choose some direction. This is the n hat direction, this is the m hat direction. Well, in this loop integral, I have contributions from the four sides. But as I set d go to 0, there are no contributions from these sides. this, let's call it h. So this integral in the limit that d goes to 0 is basically the electric field outside minus the electric field inside in the m hat direction times h as d goes to 0. But b dot ds well, as d goes to 0, the area goes to 0. So I'm multiplying the magnetic field with 0 area. So unless the magnetic field is infinite, well, the magnetic field is always finite. Since magnetic field is finite, if I multiply it with an area, I get 0. Basically, the addition of this term doesn't really change the continuity property of the component of E parallel to the surface. So I just combine these two, and we obtain that E outside dot m hat should be equal to E inside dot m hat. Well, taking the scalar product with m hat just gives me the direction in the component in the direction of m hat. M hat is basically any vector that is parallel to the surface. So the parallel component of the electric field is the same inside the surface and outside the surface. So we already had this property in electrostatics. Now we see that we still have the same property in electrodynamics, although we have changing magnetic field which induces this new kind of electric field. Still, the parallel component is continuous. Well, this is any E. In fact, you see, what the total electric field should satisfy this equation. There's a surface. Well, it can be a real physical surface, like the interface between two different materials, or it can be just an imaginary surface. For example, in our case, it's the surface of the solenoid. We have inside the solenoid, outside the solenoid.
Hocam bir şey soracağım. Şimdi biz burada B dot ds'i hani kapalı yüzey için şey yaptık ya.
No, it's not a closed surface. You see, loop is closed. The surface is open.
Peki şu integrali nasıl ona eşitledik?
This one.
Yok altındaki. Çünkü bu closed.
No, sorry, it's not closed, it's open. It is this surface over here, it's an open surface. It's not a closed surface. This is a rectangle. Of course, electric field has both parallel component and perpendicular component. Of course, I'm not saying that the electric field is parallel to the surface. What I'm claiming is that in general, for an arbitrary electric field, it can be pointing in any direction depending on how you create that electric field. What I'm saying is that that electric field has a component parallel to a given surface, and that component has to be continuous. I don't know about the component perpendicular to the surface. Well, it will depend on the surface charges. Well, you see, even the static electric field need not be perpendicular to the surface. You see, just imagine this case. This is my surface, arbitrary surface. I have a charge plate over here, another charge plate over here, finite. So the electric field, well, it will have some arbitrary angle with my surface. I don't really know. But in a sense, you are right. You see, we have the E that the curl of E is equal to minus dB by dt. You can always write the electric field as the electric field due to point charges plus the electric field that is induced by a changing B field. Yes. Exactly. Not necessarily. I mean, the electric field can be any source. The surface can be any surface. It can be the surface that's creating the electric field. It can be just part of this. It can be contributing to the electric field. It might be neutral, etc. But the parallel component of the electric field across that surface has to be continuous. Now, in general, the electric field, we can separate it into two parts. There is the electric field created by the point charges and the electric field that is induced. Well, even this separation kind of gets kind of fuzzy when we study moving charges. But even if we assume that we can make this separation, curl of the electric field of point charges is 0. And curl of the induced electric field is equal to minus dB by dt. Now, don't miss this point over here. You see, if B is constant, B dot ds is a constant, so this term is absent. If B is changing, then this term in general is not absent, but in the limit that we are studying this continuity, it doesn't contribute. So basically what we have stated over here is this one, not the rest. The rest we had done, I don't know how many times. The crucial thing is this part over here, that this additional term on the right-hand side doesn't change the continuity property of the electric field across a surface. This is always true for an arbitrary electric field. And for the parallel component, the change will be proportional to the surface charge, that's if there are any surface charges. Okay, let's give a break, and then we will continue in 10 minutes.